So, having discussed this unconventional D wave pairing, we let us now look at a model which can give rise to this D wave pairing, a mathematical model which is also relevant for these superconductors which show D wave pairing. We have to write down a model almost with the kind of knowledge that we have about electron correlations and so on, and we introduce this model as a TJ model. So, we say that demonstrating different pairing symmetries. And we write down what is called as a TJ model. And at this moment we write down without any double occupancy constraint. Let us first write down the model and then we will discuss various issues related to it. So, the Hamiltonian is written as H equal to minus T and a Ci sigma dagger Cj sigma plus a Hermitian conjugate, which is a usual kinetic energy term. The sum is over the nearest neighbor I and j sites. Sigma refers to the spin, and we have a spin-spin coupling which is known as the Heisenberg coupling. We have seen that how this spin-spin coupling can actually arise. Maybe we will see it in a tutorial how one can actually get a spin-spin coupling, and we write this as Si dot Sj minus 1/4 Ni Nj. This is just a constant term that is added, and we also add on-site repulsion term which is given by Ni up and Ni down. So, just to tell you about the various terms in this Hamiltonian, this is called as the kinetic energy, which is the hopping of electrons. So, this the one with not a dagger, so this is called as a destruction operator. So, it destroys a particle with spin sigma at a site j, particle means a fermion, and creates the particle at site I with a spin sigma. So, basically so there are two sites I and j, and there was a spin, say sigma, let us call sigma to be an upspin here, and this operator operates on such a state and moves this spin to here, and then in the next step this is considered as j and this is considered as I, and then one has well, I mean I would be probably here and so on. So, maybe this is not let us not write this as I. Okay, so I would be a site which is here then in the next thing, and then it will keep moving it by again application of this operator and so on. So, this keeps moving the electron from one side to another, and this is called as the hopping term or the kinetic energy term, and the Hermitian conjugate is mandatory to add to give us a real eigenvalue for the Hamiltonian. The next term, which is Heisenberg like term, spin-spin interaction. So, this term is not written in terms of the fermion operators, but later on it will be written in terms of the fermion operators. It will be written in terms of the spin operators at site I and j, again I and j are nearest neighbors, and these are the densities at site I and j. So, there is a spin-spin coupling between the spin vector at I and the spin vector at j, and these are vectors. So, they have components x, y and z, and that is why it is called as a Heisenberg spin-spin interaction. We could write it in the Ising sense, that is, this has only z component, and still can write down a similar Hamiltonian, which is what we will show in a tutorial, and this is called as the Hubbard repulsion. Please take a note as this term. This is a term that involves density of an upspin with which is an upspin density is interacting with a downspin density at a given site I. So, if u is large, it will not allow, or rather it is becoming energetically unfavorable to have a spin down when there is already a spin up at a given site I, or the vice versa. So, this actually brings in the electron correlation, strong electron correlation, that is if the electrons are strongly interacting, this site will not allow double occupancy and so on. So, basically what we mean to do is that we want to solve this Hamiltonian. Now, this Hamiltonian does not have an exact solution, at least for 2 dimensions that we are looking for, and we need to sort of make simplification. But at this moment, in order to show D wave pairing, we do not really need to solve this Hamiltonian. We can just write this Hamiltonian and explain, as I have explained, various terms to you. So, this is a model for an interacting fermionic system. In principle, in any dimension, we are only interested in dimension equal to 2, d equal to 2, because of the reason that these high Tc or the high temperature superconductors are actually found in 2 dimensions, or rather the planes which are responsible for superconductivity are 2 dimensional planes, which are copper oxide planes. In order to simplify this Hamiltonian to get to a more meaningful form, we will have to do a Fourier transform of this. But before that, let us write down the Tj model, which one is familiar with, where we can write down this as a T and a Ci sigma dagger with a tilde and a Cj sigma and a plus a j Si dot Sj minus 1/4 Ni Nj. That is it. So, what we have done is that we have replaced these operators, we can also replace these operators and so on by their tildes, and have neglected the last term, which is the Hubbard repulsion, means that this is implicitly taking into account, or rather this is explicit if we do it. So, explicitly no double occupancy constraint. So, the definition is that the Ci sigma tilde is equal to Ci sigma 1 minus Ni sigma bar. So, that automatically says that if there is a spin of sigma bar at a given site I, so this Ci sigma will be equal to 0, which means that you cannot have another spin coming there with a spin sigma, or with an electron with a spin sigma, and so on. And this j is equal to j plus 4 t square over u, where u in the limit u going to infinity, then I mean this j tilde is equal to j. So, in order to do further simplification to this model, let us write it down in the momentum space. one gets. So, H is a function of k now, it becomes somewhat slim, the kinetic energy becomes somewhat simpler, and the terms which are the other terms, we are still writing the original Hamiltonian and not the Hamiltonian that we have written down in the form of TJ model. So, we still have a u term there. There is a gamma alpha beta gamma mu nu minus delta alpha beta delta gamma mu, and there is a ck 1 alpha dagger c k 2 beta and c k 2 minus q mu c k 1 plus q gamma. So, this is the second term. This you have to do it very carefully, where each of those C I sigma is converted into sum over k. So, this is C k exponential I k dot r I and so on. So, use this and use those momentum conservation, and you will be arriving at this. So, this is something that needs to be used, and there is a u and then there is a k 1, k 2 and a q. So, these are the three momentum indices that are required here, C k 1 dagger, C k 2 down dagger, and C k 2 minus q down, and C k 1 plus q up. Now, it is very easy to see that there are only singlet pairings available, because the pairing, if this is a model for superconductivity, that is, if this model can give rise to superconductivity in for some parameter range T, J and U, then this has only the singlet pairing is only encoded in this model, and there is no triplet pairing, and neither we are interested in triplet pairing, as we have told in the last discussion. We only want to concentrate on the singlet pairing and only finite momentum singlet pairing, and that too the D wave pairing, which is L equal to 2. And in order to do that, let us write down the definitions of epsilon k for a for a two dimensional square lattice. So, this is equal to a minus 2 t, where t is the strength of the hopping, and a cosine k x a plus a cosine k y a, and a j q is equal to a j and a cosine q x a plus a cosine q y a. We can take a equal to 1, which is a lattice constant, and then can in principle forget about. So, a is equal to the lattice constant, a is the lattice constant, and we can simply ignore that from later on. Now, here of course, the q is equal to k minus k prime, or which is here. I mean there is a k 1 and a k 2, and then a k 2 minus q and k 1 plus q, and there is of course a k 1 and a k 2. So, it is basically either you call it a k 1 minus k 2 or you call it a k minus k prime. We could write in principle in terms of in terms of k and k prime, just wanted to write it in terms of k 1 and k 2, but in any case the q, the momentum index q is actually for the transferred momentum, and this one now we need to understand a few things, how to resolve this according to the symmetries of the 2D square lattice, and write the interaction term in a more meaningful fashion, such that we can get the D wave superconductivity out. So, I reiterate that having Fourier transformed the Hamiltonian, which is a TJ model, we have still kept the which is a tunable parameter. If u is very large, then of course it won't allow W occupied sites. So, they will project all the W occupied sites from the Hilbert space, which is what the TJ model is, which is written in the last slide. And having written the Fourier transformed Hamiltonian and these definitions of the spin dispersions or spin wave dispersions and the electronic dispersions, we need to understand that how to get the interaction term which can cause superconductivity. So, in order to do that, let us look at a little bit of group theory, and since this study of group theory will be outside the ambit of this course, neither we want to do it very elaborately. We will give you the basic things and basic ingredients that are required for our purpose, and write down the interaction term in terms of various symmetries or various basis functions which come from the irreducible representations of a symmetric group, a discrete symmetric group that is relevant for a 2D square lattice. So, let us write as symmetry considerations. Let us write a square and let us just mark some points. So, this is your y and this is your x, and this is the square ABCD. We know that it has certain symmetry properties, that is, if you rotate it by 90 degree in the clockwise direction, then A will go to B, B will go to C, C will go to D, and D will go to A. However, the square remains invariant, is just renaming of this vertices that will take place. So, we are going to take 8 points which are these, we will call them as so, these are the 8 points which are taken on either side of this the axis that is that are marked here. So, let us call this as 1, this as 2, we will tell you the reason for writing this, 8, this is 6, this is 3, this is 7, and this is 4. So, this has well, this is 3, I am sorry, this is 5. So, this is a p x q y, that is the coordinate of this, where p and q are some numbers, and this is p x minus q y, this is q x minus p y, this is minus q x minus p y. This is p x minus q y, this is minus p x q y, and this is minus q x and a p y, and this is a q x and a p y. So, this is how the 8 points are labeled or they are marked, and so there are these 1 to 8 points shown in the above figure. They correspond to certain basis functions which we will see. Now, let us look at the symmetry operations that leave this square invariant. So, one is called as E, the identity operation, which of course leaves anything invariant, you just multiply it by 1. Number 2 is C4. So, rotation by 2 pi by 4. So, this if it becomes C n, it becomes 2 pi by n, since it is 4. So, which is equal to pi by 2. So, that is another operation which I have already said. C4 square, which is rotation twice. So, rotation by pi rotation thrice. So, it is rotation by 3 pi by 2. Rotation C. Now it is a reflection about the x axis. So, let us call it as mx, reflection about x axis. 6 my, it's a reflection about y axis. Seven sigma u, let us call this sigma u to be the diagonal, which is a BD, and a sigma v to be a diagonal AC. So, the reflection or inversion, reflection about diagonal, say BD, and finally, the last one sigma v. So, reflection about diagonal AC. Okay. So, these are the 8 symmetry operations that leaves the square, the 2-dimensional square unchanged. It will simply be probably 1 will go to 2, 3 will go to 4, and 4 will go to 7, and things like that. Let me show the one operation which, so for example, you can test it yourself. A C4 on 1, 2, 3, 4, 5, 6, 7, 8. So, if you apply the C4 operations, then what happens is that 1 becomes 4, and then 2 becomes 1, and then it becomes 2, and then it becomes 3, and then it becomes 7, then it becomes 8, and then it becomes 6, and then it becomes 5. So, and then you can work out that what happens when you apply a C4 square or a C4 cube or a mx, my, or sigma u or sigma v. So, these are the symmetry operations which leaves the square unchanged. Now, this is quite arbitrarily we are writing down character table, and a full knowledge of group theory is required, at least for limited knowledge with discrete groups, and which you can get in this book by A.W. Joshi, which talks about the symmetry groups. So, let us write down the character table of. So, this is called as a C4V symmetry group. So, we are going to write down a character table for the irreducible representation of C4V. So, if we so this is the irreducible representation, and this is the identity. This is C4 as we have discussed. This is C4 square, this is C4 cube, mx, my, and we need 2 more for sigma u and sigma v. Okay. So, the different irreducible representations they are these representations are gamma 1, gamma 2, gamma 3, gamma 4, which are sorry, this is gamma 4, and there is a all these are one dimensional representations. Gamma 5 is the only 2 dimensional representation. So, these representations under these symmetry operations, they the values they acquire in the character table are, as I told, that you need to look at the C4V symmetric group in either in any book or in this book by A.W. Joshi, which presents a very clear description of this symmetric group and many others actually. So, these are all ones, and there is a 1 minus 1 1 minus 1 minus 1 minus 1 1 1. This is 1 minus 1 1 minus 1 1 1 minus 1 and a minus 1, and 1 1 1 1 minus 1 minus 1 minus 1 minus 1, and these are the 2 dimensional representations 1 0 0 1 0 1 minus 1 0 1 0 0 minus 1, sorry, this is minus 1 0 this 0 minus 1 1 0 1 0 0 minus 1 minus 1 0 0 1, and 0 minus 1 minus 1 0 and 0 1 1 0, and so on. So, these are this is the character table for this symmetric group, but what is more important to us is the following: the basis functions of C4V, and so these are the irreducible representations, and then we have 2 3 4 irreducible presentation of this C4V. The basis functions transform like gamma 1, this is 1, this is gamma 2, it goes like x y, gamma 3. This is what is important to us, the x square minus y square. This what was told yesterday, that f x y was taken as x square minus y square, a gamma 4, which is x y x square minus y square, and this gamma 5 is written as this. In fact, it is not important, the two dimensional representations are not important. What is important for us is gamma 3, which is related to this the d wave what we have seen earlier. Now, let us go back to this ongoing discussion on this, and in fact, if you do a k space representation, this actually looks like a cos kx minus cos ky, and of course, these there are other two dimensional representations, rather there are other singlet representations which we will be talking about. So, let us look at the term that comes with. So, so the singlet, so the interactions. So, we refer to the 3 slides back when we wrote down this this Hamiltonian. Let us call this as equation 1, and if you want this as equation 2, and this as maybe this as equation 3. So, from equation 3 we write down the interaction term. Okay. So, the in the singlet channel we have V s this is equal to 2 j q. It is important to note that this 2 factor is coming from the sum over all spin indices there. U is the on-site term, and the other one has a k dependence or q dependence. This is in the singlet channel, and in the triplet channel, which of course would promote an up or a down pairing, and nothing in this Hamiltonian that promotes a up or a down pairing. It is always a pairing between an up down spins, and hence this is 0. And let us write down the term which is a cos a q x plus a cos q y, which is coming from the j q term. So, this is equal to a cos of a k x minus a k x prime plus a cos k y minus a k y prime. So, this is like a half of a cos k x plus a cos k y cos of k x prime. So, basically this can be expanded, which I skipped one step, is cos a minus cos b, cos a minus b plus cos of c minus d, and if you combine all the terms and then do a sort of simplification, then this thing comes. As told earlier, that we have taken the lattice constant to be equal to 1, and so there are terms such as a cos k x minus cos k y and a cos of k x prime and a cos of minus a cos of k y prime, and we can also take of course a k x, a sin k x prime, and a sin k y sin k y prime. So, this is the so this j q. So, this is nothing but the j q without the j factor. Okay, we can write down the j factor if you like. So, there is a j. So, there is a j, and this is like the j q equal to this. So, there is a j there and so on, and so we have a j here. So, we have seen these things. So, cos k x plus cos k y This transforms according to the A1 representation. Again, you have to refer to the group theory book by A. W. Joshi or any other group theory book. It will give you what the A1 representation is, and for our case it is known as the extended S wave. Cos kx minus cos ky, it is a B1 representation, and as said earlier, this is called as the D wave. And sin kx, sin ky, this corresponds to the 2D E representation. And this is called as a P wave. Okay. So, the interaction term in the, so let us write down the, which are allowed symmetry channels. Is a V on site is a S wave, and that is equal to U V extended S wave, which is equal to minus j cosine of kx plus cosine of ky cosine of kx prime plus cosine of ky prime. You remember that when we derive BCS theory, or V k k prime was taken to be equal to minus V 0 for all k and k prime, provided the energies of the single particle energies lie within a thickness or a energy shell of h cross omega d just outside the Fermi field Fermi C. Here of course, this condition is not satisfied, condition is violated, that is we have a k dependence or a k minus k prime dependence coming in the interaction term, and V in the dx square minus y square channel. As we told that this is what is going to be most important and interesting for our case. So, luckily that comes in this model, and that is why we have actually considered this model. It is a cos kx prime minus cos ky prime. So, we can write down the V k k prime now, it is equal to a u delta k k prime, that is precisely the same as what we have seen in BCS theory, excepting the fact that there we needed specifically an attractive interaction for superconductivity to occur. However, this U is purely repulsive, and it may actually come or has a, it may have a large value which encodes strong electron correlation into the model. So, this is there, and then we have J F S. We are only talking about, we are leaving those P wave representation or two dimensional representation. It is only in the so this is only in the singlet channel, rather and these are even symmetry. If kx goes to minus kx, it does not change sign. So, this is called F S star. We write down. So, this is with a just on site S wave, and this is the extended S wave. So, this is your F S k, and this is your F D k minus j f d k f d k prime, and that's the interaction term. And as told earlier that, so this is a extended S wave and this is a D wave. Okay. So, V k k prime indeed depends upon k and k prime, and it luckily it depends in a product form of k and k prime. So, they get decoupled and that causes a lot of simplification. So, we will put this, we will not solve it further, but we have been able to show that this model can give rise to D wave correlations, and this is probably very relevant for the study of this high Tc superconductivity. So, if we write it down even without much thought into the BCS gap equation, now one can solve for. So, this is the gap equation. If you look at your earlier notes or discussion, you will see that this is the gap equation. Now, this gap equation V k k prime is precisely what you have written here. So, if you put this V k k prime, if you put this V k k prime into this equation, this gap equation, one can actually solve for each of those symmetries, namely the. So, one can actually make an ansatz for the superconducting energy gap this corresponds to the on-site S wave, this corresponds to the extended S wave, and this corresponds to the D wave. So, each one of them and according to this irreducible representation. So, these are the basis functions in the K space for these representations, and each one is actually orthogonal to the other, which can let us write that delta k is equal to a sum over k prime u delta k k prime minus j of f s star k f s star k prime minus j f d k f d k k prime, and so this and then multiplied by the delta 0 plus the delta s star f s star k plus a delta d f d k and so on, and then of course, there is a 2 f e k prime and a tan hyperbolic beta e k prime, where of course, your e k prime is equal to root over epsilon k minus mu plus a delta k square. Of course, this tan hyperbolic would come here. I mean, it is not in the denominator, it is in the numerator. So, this is in the numerator. It is a highly nonlinear equation, and there is no way other than resorting to numerical techniques for solving this equation. But the good part is that you will also have to write this delta k in this part of this equation, and then use the Fourier trick, that is, you try to make these each write down these equations which are coupled equations and set of basically set of 3 coupled equations. Which are to be solved self consistently for choice of u, j, and for u, j, and of course mu, and t is of course 1. I mean the hopping term t is equal to 1. The solution yields a delta 0, delta S star and a delta D, which are what we want, which are the gap functions in this particular symmetry channels, and these give the information that how this as they fall off as a function of temperature. If you remember that this is what we wanted to do, and in any second order phase transition, so these are the gap parameter or the order parameter for each of those, and these actually fall off as t, each one of them. We have seen in the BCS theory that we had a single delta. So, we did not have to solve 3 coupled equation, it was just one equation. Now, because of this emergence of new symmetry channels, we have 3 symmetries particularly which are important, which are S wave and extended S wave and D wave, and then which has to be solved for each one of those delta 0, delta S star and delta D, and it has to be solved as a function of t for these choices of u, j and mu, and this gives the T c delta as a function of T c, and this actually completes the problem of finding the gap function and finding what is T c. And as we have emphasized a number of times that the energy gap is the most important thing in superconducting problem or in the study of superconductivity, and this is what it aims to do. It is true that we could not solve this problem like sitting here, because it involves a very highly nonlinear equation, solution of nonlinear equation. You could try a Newton-Raphson method, but these are coupled equation, they have to be solved self consistency also for these choices of u, j and mu which are left to you to choose, and the values, as I told, that the u has a value which is large and j has a value which is given by I mean basically it is typically much lesser than u because there is a form that we have shown is j equal to some j tilde equal to j plus 4t square by u. So, one could representative value of this can be shown as say u equal to twice of bandwidth. It is a square lattice, it has a bandwidth of 4t because it is 2t cos kx plus cos ky. So, it is 4t 8t. So, if we take it to be the bandwidth, then j should be much smaller and j should be maybe maybe a t or even lesser than t, maybe half t or something, but of the order of t, and mu can be taken to be any value because this is a solution that we want to believe that it is true for small electronic densities. It does not have to be. In fact, small if you take the electronic density to be large, then the solution converges faster. So, you could take it to be a value which is say minus 3t or something. The t can be set equal to 1, and then you have 8, 1 and minus 3 as the various parameters, and if you wish to try this solution, you could try that, and one should get a behavior like this, that these gap functions individually would vanish at a temperature which is demark or rather distinguishes the temperature for this particular transition in this symmetry channel, which is given by this Tc.